Okay. So we start with lecture 19. And actually, I had went on talking on lecture 18 without realizing that the video has stopped. So I'm repeating all that I said. Only thing you don't know what I said. Right. So we are in lecture 19, and we did talk about porphyritic texture, flow structures, globular porphyritic textures. Now there is another thing that happens here, which is best visualized in a binary eutectic system. It is that this point, this is the place where you have eutectic crystallization. What happens in this field? Two crystals co-precipitate. Two crystals co-precipitate. Now when this happens, you can imagine you have a melt and you have two crystals co-precipitating. Either these two phases, so when you precipitate, there are several things. I have not gone into the details of this because it's a little, it takes some more time, and I just don't have time in this coursework. Just no freedom to do the way I would like to do. So I have to sort of sometimes truncate things. There are two things that happen. One is the nucleation of a crystal. It's a very, very difficult thing. It's like a child being born in the womb of the mother. It's a very, very difficult process. It requires bonds to be created, materials to be brought in at the nucleation site. It requires a very complex structures, and it's a subject by itself. So we have what is called nucleation of a crystal. So how many crystals will nucleate? And then we have, if the crystal will nucleate, how large will it grow? So there are two things, a crystal nucleation and crystal growth. Now these are very complex things. Just to make it simpler, so minerals that have, see, all silicate minerals have SiO4 as the tetrahedra. SiO4, AlO4 tetrahedra. That's the basic polymer forming framework in all silicates. Right? You know it has a covalent, 60% covalent structure, 40% ionicity. And the problem is about, you know the SiO4 tetrahedra has 4 negative charges, and these negative charges are balanced by cations so that the mineral becomes electrically neutral. Now what happens when you grow complex minerals that involve multiple sites growth and elements to be accommodated in multiple sites, especially aluminium silicon substitution that we have talked before? These minerals have strong inhibition to growth. So what they do is, they do not grow too big, but they nucleate. Because they're very complex, they nucleate in many nucleation zones. Whereas minerals like olivine or pyroxenes, for example, which is NgFeSi2O6 or NgFeSi2O4, where magnesium and iron can exchange, and the diffusivity is very high. The diffusive flux between magnesium and iron in the crystal and in the melt, they're very high. They have high crystal growth. So they can afford few nucleation sites, but larger crystals. So elements that normally can exchange and diffuse very easily through the melt, as well as through the crystals, they tend to grow to larger sizes from a fewer nucleus. Whereas minerals, which involve diffusion of more aluminium and Si and low diffusivity elements, they tend to nucleate in more spots and do not grow to larger sizes. But as you can understand, if you have higher temperature, these things get offset. But generally, it is found that overall it's true, where there are fast diffusing elements, they form smaller nucleations and larger crystals. Whereas minerals that have less diffuse, elements that are less willing to diffuse across crystal melt interfaces, they tend to form more nucleus but smaller crystals. Viewed in this perspective, if I look at this crystallization, say from a melt at this point, and you precipitate both A and both B, then the chances happens that, say for example, if A say comprises highly diffusive elements, and B contains low diffusive elements, then the chances are, low diffusive elements, then the chances are that B will form more nucleation zones and smaller crystals, and A will form fewer nucleation zones and larger crystals. So sometimes you can come up with situations, and it's a fairly common situation, that you have so this is B and this is A. The minerals with highly diffusive elements, they grow to larger sizes, and elements which have low diffusive elements, so the crystal melt interaction is not so fast. So what happens? They make more nucleation sites and they grow to smaller crystal. So what happens? When you have both A and B precipitating, you can have a situation that crystal A grows from a fewer nuclei and then grows bigger, but B crystallizes into smaller crystals and ultimately get engulfed within the larger A crystal. This is classic case of cotectic or eutectic crystallization. This is a classic case of eutectic crystallization, where two minerals grow simultaneously but having different nucleation rates and growth rates. And this is very typical for this eutectic crystallization. So you have this type of textures. So one texture is famously called ophitic texture, O-P-H-I-T-I-C, ophitic texture. What does this involve? It involves a mineral which is clinopyroxene. I'm giving you the name here, clinopyroxene. The formula for that mineral is CaMgFeSi2O6. In brief, this is called clinopyroxene CPX. Why it's called clino? Because it crystallizes in the monoclinic system. Your teacher in crystallography and mineralogy should be telling you all about this. Monoclinic, triclinic systems, etc. So you have clinopyroxenes which completely to partially enclose a mineral which I have already told you is called plagioclase. So this is called an ophitic texture. So an ophitic texture essentially represents eutectic crystallization, where the mineral clinopyroxene, which is equivalent to A, grows in fewer nucleation sites and has a faster growth rate, because magnesium and iron can diffuse very fast, whereas plagioclase, you know from my earlier studies, it's NaCl-AlSi. That exchange and diffusivity across the crystal melt interface is very, very slow. So those minerals form numerous or more nucleation zones, but do not grow to very big sizes. So So what happens? You generate what is called an ophitic texture, which is an example of eutectic crystallization of clinopyroxene and plagioclase, where clinopyroxene is similar to A and plagioclase is similar to B. So this is a very classic texture that you can see. The occurrence of this texture tells you that your melts crystallize finally in the eutectic system. In the eutectic, as eutectic melts, it crystallizes from the eutectic melts. There are some other few textures. So sometimes what happens, say for example, if you take the melt composition L0, and you can see that your early formed crystals are A, and then finally B is added to A. So what has happened, if you follow how the rock is, the fraction of A increased dramatically, increased very fast, and at some point plagioclase is joined with or B joins A for co-precipitation in the eutectic proportion. That is what it does. So first you have precipitation of A, pure A, and A only, and only after substantial part of the magma has crystallized, B precipitates in the proportion of the eutectic with it A and adds to the A and B into the crystal side. So what happens initially when A crystallizes, a large fraction of the magma is completely, what should I say, is a large part of the magma is filled up with A. Large part of the magma is filled up with euhedral phenocrysts of A. And when B joins A and co-precipitates, then the amount of void in that crystal, in the crystal mush, if I can say, MUSH, in the crystal mush, the amount of void is little. So what happens essentially, your major framework is done possibly by A. These are the crystals, early formed A crystals. These are grow to large sizes, and they are, as I told you, euhedral in shape, and they may be randomly distributed, depends on how they form. So this produces crystals of A. But in between that you have these spaces. In between that you have these spaces, like these spaces. So what happens? The co-precipitation of A and B now occurs in this space that is left by the early formed crystals. Have you understood? So after substantial part of the magma has crystallized A, and A forms a very thick, a very good crystal mush within the magma. That means the melt fraction has decreased quite a bit. So the A crystals are now in grain contact, making up some sort of a framework. And in between, you have open spaces where there are melts. And when these melts crystallize to A and B, what happens is that this A and B normally cannot grow to their proper size. That means their growth into euhedral crystals become inhibited. Have you understood? So these crystals, late stage crystals that are crystallized from a magma, late stage crystals, they are seldom euhedral in shape. They are normally subhedral to anhedral in shape, because they have to crystallize, but they have to crystallize in a space already defined by the early formed crystals. So what you get is, here you can get crystals of A and B, but these crystals seldom go to their, seldom have euhedral shapes. Now, so what happens is, here you have smaller crystals of A and B in a network like situation where you have A and B that precipitates. You may also have ophitic textures in these places. So what this texture, this type of texture, where the major framework is done by the early formed crystals, leaving an intergranular space that are filled up by later formed crystals, which are mostly subhedral to anhedral in shape, and this texture is called intergranular texture. Intergranular texture. So you can imagine intergranular textures are common for plutonic rocks, because in plutonic rocks the magmas crystallize slowly at depth. Intergranular texture is not a classic texture of lava, that volcanic rocks from lava flows. It can never be, because if it is filled with crystal, if a magma is filled with crystal, then it has very, very high viscosity. And such high viscosity melts cannot rise up so fast. Because when the melt is less viscous, when you add crystals, the viscosity of the system increases. So as you decrease melt fraction or you increase crystal fraction, the viscosity of the melt increases dramatically. So highly crystal rich melts are highly viscous and they're not capable of flow. Whereas magmas that have low crystal fraction or low crystal fraction, such magmas have lower viscosity and they are capable of flow. So if for intergranular textures to happen, you need magmas to crystallize to great extent. So that's a classic example of plutonic rocks. Intergranular textures are typical for plutonic rocks. They are not typical for volcanic rocks. But porphyritic textures, glomeroporphyritic textures, these are very, very typical of both volcanic and plutonic rocks. Now, I bring you to another type of textures, and this is interesting. I told you in a simplistic way that euhedral crystals form where the crystal fraction is small. That means much of the magma has not crystallized. Then the chances of getting euhedral crystals are more. But anhedral and subhedral crystals, they form in melts that are substantially crystallized, or they typically form in crystal-rich magmas. That means they are characteristic of plutonic rocks. If you have a lot of crystals which are anhedral or subhedral in shape, these are typically, mostly, plutonic rocks. Volcanic rocks require a lot of magma to flow out, and so you don't get anhedral or subhedral. Anhedral crystals you never get. You get mostly euhedral or some subhedral crystals. But anhedral crystals you don't get because the fraction of crystal is very small. But I will tell you now of mechanisms by which subhedral and anhedral crystals also may form in magmas. And this I will tell you how it is done. I will tell you in terms of binary eutectic system. Now, the basic premise of drawing the phase diagram that I will is that the melting temperature of minerals, you remember in your eutectic system we took pressure as constant, or low pressure or pressure as a constant. We did not vary the pressure. But almost all minerals, the melting temperature of the mineral increases with pressure. So higher the pressure, higher the melting temperature. So if we do this, then we can draw a phase diagram like this. You must understand here that a magma moves from greater depth to lower depth. Never the reverse process. You cannot have a magma going from a low pressure to high pressure. You have a magma which comes from greater depths to shallower depths. Now, let me draw a phase diagram where I actually superimpose, let's say this is A and let's say this is B. This is weight percent A as always, and this is temperature of melting of A, and this is temperature of melting of B. And I'm just drawing the liquidus, so it's something like this. Let's say this is low pressure. This is low pressure. Now, at higher pressure, the melting temperature of A increases, let's say to this. This is TMA, but at higher pressure. And this is TMB at higher pressure. And so from this, you can generate a situation where it is like this. So this is high pressure liquidus. This is high pressure liquidus. There are three parts to this diagram. One is this part and this part. Here you see in this part, high pressure liquidus of B is followed at low pressure by low pressure liquidus of B. On this side of the diagram, the high pressure liquidus of A is followed downwards by high pressure liquidus of A. But in the middle, which is defined by the two eutectics, high pressure liquidus of B, liquidus of A. So there are three parts. Let us take either, if I won't take this part, I will leave it to your own imagination. I will take either this part or this part. Let us take this part. There's a lot of free space, nothing else. So let's say I start with the magma and I start with a black pen. I start with the magma having this composition, say L0. I start with the magma at this composition. So it's at high pressure, I have to take this diagram into consideration. The high pressure liquidus diagram in red. I take this part of the diagram as relevant to our discussion. So as the liquid is cooled, at this point, the temperature of the melt coincides with the liquidus of B at high pressure. So immediately from this point, solids will start to crystallize. Solid means here B will start to precipitate. And as B precipitates, as we know, the liquid composition moves here and you have more solid B. So you have solid B crystallized at high pressure crystallization of the melt L0, and we have this much of B, and for example you can know this m by n. M divided by n plus n is the fraction of melt. M divided by m plus n is the fraction of the melt. At this point n is equal to 0, so it's totally melt because the fraction of the melt is 1, m divided by n. Now we know this. Now, this is happening at greater depths, that means higher pressure. Now say, by some mechanism, so before we do that, we will quickly draw a diagram here just to remind us what happened. So you have nice crystals of A in a magma. These are euhedral phenocrysts of B. Euhedral phenocrysts of B in a magma. That's how it is. The magma is not floating, so it's random. The crystal is random. Now what happens is, let's say by some mechanism, the magma gets access to a conduit, but that conduit does not take it to the surface of the earth. So it doesn't erupt as a lava flow, but the whole magma chamber comes from a greater depth and gets ponded somewhere below the ground, but at a lower depth. So if you do that, then now when the magma has ascended to a shallower depth, this diagram now becomes valid. Have you understood? At high pressure, this diagram was valid. But as the magma ascends, the lower pressure eutectic phase diagram becomes important. If you do that, then now you see, forget this red line now, because we are no more at the high pressure, we are in the low pressure. And this diagram becomes valid. Now, with respect to this diagram, you see, this is my melt composition now. This is the melt composition now. But, your crystals of A here, crystals of B, above P and B, crystals of B cannot survive. They have to be in the melt. There is no stability with respect to this low pressure eutectic. All the B should go into the melt. If you allow enough time, all the B shall go into the melt. So what happens? But if you do not give time, then the whole of B cannot go into the melt. Whole of B cannot go into the melt if you do not give enough time. Now you see the complication arising here. See, with respect to the low pressure, B should not be stable as a crystal, but should go into the melt. If you allow all the B to go into the melt, then your melt composition is back to this point. If you allow all your B to go into the melt, then your melt composition is here. All the B will go. All the B will remelt. Now, when this remelting occurs, then if you take a crystal, the first things that go into melt are the corners. The first things that go into the melt are the corners because of high surface energy. Have you understood? So what happens when melting starts to occur? The corner starts to melt first. So what happens after some time? Your B crystals looks like this. And this part is resorbed back into the melt. So what crystal do you have here now? Anhedral crystal. But this anhedral crystal did not form, was not forming. This was an earlier crystal which was resorbing or remelting. Have you understood? So this is called a resorption texture. It's called a resorption texture. So this anhedral shape of B is not because B develops this because it's crystallizing and the available space prevents it. No. It had formed as a new hedral crystal. But then, because it starts to bring from the corners and the sides with a higher surface energy, it has been brought into this anhedral shape because of remelting, not crystallization in a confined space. So these are called resorption textures. Now you can imagine, if you have a crystals, and because you now in this eutectic diagram, this was your L0 melt composition, and this is your new melt composition, as more and more B go into the melt, this composition migrates to the right, and so you will produce a melt. If all of the B go into the melt, then the composition of the melt will be the same as the initial composition. But if part of the B does not go into melt, then your initial melt composition will not be L0, but will be between this and this melt composition. Have you understood? Between this and this melt composition. If all B had gone melted, then you will get back your initial melt composition. But if your part of your B remains in contact with the melt, then you will not get the initial composition, but somewhere between this composition and this composition. It will depend on how much of the B went into resorption. Have you understood? So now we have come to a complete question. So if you do not allow, say for example, your change from high pressure to low pressure was quite slow or fast. If it was very fast, then all of the B will not be able to go into melt. And a part of the melt and part of the B would remain. And so your grain shape now will be like this. Your grain shape now will be something like this, your grain shape. But when this melt with these resorbed crystals reach the liquidus, then new B crystals will form. New B crystals will form at the low pressure. Right? So, if that happens, what will happen? You had the pre-existing B. So the chances are that your old high pressure B will give it a good nucleating base for the new low pressure B to crystallize. So what will it do is, it will crystallize into these shapes, and you will start your crystallization as before and reach this eutectic, then it will follow the same path. But what is important is that this crystal B has two parts now. One is this low pressure part, crystalline, and the relict high pressure How will we differentiate? It is very easy. What happens along these margins of the grain? Along these margins of the grain, there are small materials, droplets, say melts, for example, quenched melts. They form small minuscule droplets and they sort of border your old high pressure B, but the new low pressure B does not have that, and so you will have this crystal. So now here you have an anhedral crystal of B, but it has a much more complex history. It had an early high pressure relict B, mantled or surrounded by a low pressure B. They did not crystallize at the same temperature as well. Not only that they crystallized at the same temperature, they did not crystallize at the same pressure, and they did not crystallize from the same melt composition. Because why? Because if there is a relict, then you don't get back your L0. You start, as I told you, somewhere between this and this. So this whole crystal does not have a single history. It has a multiple history. It's a more complex history. This is another way which is a very famous texture called resorption texture. And resorption texture happen different ways. Let's not get into many ways. I think we should know the basic things. Sometimes I will tell you what happens. Sometimes another way, here what I said, a magma is at depth and the magma comes up through a conduit. Sometimes it's not necessary. How can the pressure is changed? You know, magmas normally have high fluids, high amount of fluids dissolved in it. Magmas normally have high amounts of fluids. That means when you see photographs of eruption of lavas, it is tremendous amount of fluid is thrown up. Those are the fluids that are trapped in magma bodies, that very high pressure. So what happens sometimes? If you have a magma at high pressure and there is a conduit, sometimes the whole magma does not move. The whole magma does not move. The fluids above the magma, they move out. So this causes a reduction in the pressure exerted on the magma. The magma remains the same place, but because the immense fluid pressure is released, like opening a beer bottle, so the materials just squeeze out through the conduit. This reduces the pressure. So there are two ways. Either you cause the magma to move through the crust of the earth by some conduits, this is possible, or these conduits allow the fluids that are there in the magma chamber to be released as you open a beer bottle. That way also you reduce the total pressure that has been exerted on the magma. Both cases you will have the same situation. So this is what happens. You can have multiple ways in which textures can be generated. Now there is one more texture that I am left with, and I will try and complete it, although I have not taught you this phase diagram. This is called peritectic relationship. Now, I will ask you to read this from any book. I think what I will suggest to you, let me tell you, this is called peritectic melting. Peritectic melting. Or it is also called incongruent crystallization or melting, or whatever way you want to say. Crystallization and melting. Incongruent crystallization or melting. I have not taught this to you, but I ask you to study it for a binary system. For a binary system. Now, for studying this, just give me a second. Just give me a second. I will suggest you a good book. from that. Oh, can you just check the camera line and get disturbed? It's okay. So this is the book. This book is Principles of Igneous and Metamorphic Petrology. This is the book. And the authors are Anthony R. Philpotts and J. Agu, A-G-U. This is the book. And I will tell you the page numbers so that you don't have a problem. Just get me. Yes. The page number of the book is from page 201 to 204. 201 to 204. Based on what I have taught, you should find no problem in understanding this. There are many finer points on this diagram. If you find the answers, it's well. But those tricky questions I will not ask you because I have not taught you. But I want you to study page number 201 to 204 that you can study. You can also study it from the book. This is the book again. An Introduction to Igneous and Metamorphic Petrology by a person called John D. Winter. John D. Winter, you can read the book. And again, I will give you the page number. Page number, yes. And this is a good book for fractional crystallization, equilibrium crystallization. Page 97 to page 101. Page 97 to page 101. Any of this book will do. You do not have to study further than that. But I want you to study it and understand it by yourself. There is nothing for it that you will not understand. The important part of this is the one that I will talk relating to the texture. In fact, when you read it, you will see that whatever I am saying, you will find whatever there is written in the same way. Now, normally what happens, there are two ways where, A on melting gives you A solid, gives you A melt. But sometimes in nature, there's another thing that happens. So A solid gives you B solid plus melt. This is called congruent melting. This is called congruent melting. And this is called incongruent melting. This is called incongruent melting. So here, what is the difference? Here, if you melt the solid, the composition is that of the melt. Like you take a pure iron and you melt it. The composition of the iron melt is also iron. But you can have another situation where if you take a solid and melt it, you will have a new solid and a melt. But this time, the composition of the melt and the composition of the solid has to be different. That's the difference between congruent melting and incongruent melting. I will give you another example. Say you have a mineral A plus B plus C is equal to melt. That is congruent melting. But if I write A plus B plus C is equal to D plus melt, now that's incongruent melting. Because here, on this reaction, the the composition of the melt is conserved by the composition and proportion of the solids. Here, because there is a new solid, the melt composition will never be the same as the proportion and the composition of the melt. This is called incongruent melting. Opposite is crystallization. Opposite is crystallization. What is it? You have a melt and it crystallizes into A plus melt. That's crystallization. You have a melt which crystallizes A and a melt. So this melt composition and this melt compositions are not one and the same. But we are talking of melting at the same time. So one of the things that happens, or another way I can put it, melt plus A is equal to melt. That means you have a melt, it reacts with the solid and gives you a new melt. That's what is called incongruency. Now sometimes what happens, say you have, which is at equilibrium with melt. So A and B, they share an interface, AB, and it's in perfect equilibrium. But somehow, because of the nature of the phase diagram, that is what I have asked you to read, this boundary becomes unstable. So what you do is, you create a new mineral, which is B. Do you understand? You have A and melt, which was in perfect equilibrium. There was no reaction relationship. But due to the type of the phase diagram, because of the constraints of the phase diagram, at a point of time, A and melt, they develop a reaction relationship by which you form a new mineral B. Now, because the B will always be surrounding A is because the melt reacts with A to produce B. If the B was precipitated from melt, then there is no reason why B should be along the interface of A. So if B crystallized directly from the melt, then there is no reason why B should be surrounding A. But here what happens? The reaction is between, first you have an A and melt which has a perfect equilibrium non-reaction relationship. But due to the constraints of the phase diagram, a mineral B, A plus melt forms so that you have B. So what happens? This is a very famous texture and this is called it's called a corona texture. It's called a corona texture. Where an early form mineral in equilibrium with the melt develops a reaction relationship and produces a new mineral which is B. So A plus melt and you form B, but B occurs mantling the A. So what happens if the A crystal was initially euhedral phenocryst, then because of the reaction, the margins of the A start to get, so what happens? The margin of A migrates inwards. Have you understood? The margin of A migrates inward as more and more A is consumed to produce B. And as the A shrinks, the B grows inside. Have you understood? So what happens ultimately? You have an anhedral A surrounded by a coronal B. The typical example here is given by a texture, a mineral that occurs like this. I'm sorry we don't have classes, so I can't talk to you about certain things. And you produce a mineral Normally, this mineral is olivine. I have told you about this. The formula for olivine is MgFe whole twice SiO4. And the mineral that surrounds it is called orthopyroxene. And the formula for that mineral is Mg, Fe 2Si2O6. So it's a very, very common situation in plutonic rocks as well as in volcanic rocks, where an initial mineral A and melt, which had a sharp stable boundary, develops reaction relationship, and a new mineral B forms at the interface between A and B, so that the A squeezes inside because A is consumed, and B grows into the parts where A is consumed. So what essentially you do is you form a corona texture. And the classic corona texture is where you have the mineral at the core as olivine, and the mineral that surrounds it as a mantle or a corona, like that you see during the solar eclipse or the lunar eclipse. You see that you see a corona around it. This is a corona texture. What happens? What is the consequence of this corona texture is very important. Important is, say for example, a mineral A was in contact with the melt, and after some time it develops a reaction relationship where you form B, and then you see what happens. This A is physically cut off from the melt. A is physically cut off from the melt. See, this is an ideal case where you have the crystal A in the melt, but it has a nice coating of B around it, and therefore the A is now actually, although it's within a place, within the magma, it's cut off. Its communication with the melt is completely chopped off. So what happens? This happens during the case of fractional crystallization. It is indicated of fractional crystallization. Okay, I think we stop here today. You please read that section on incongruent relations in a binary system, as I showed you from the book, and I leave it to you. Either it's igneous and metamorphic petrology by Winter, as I have shown you, or by the book by Philpotts and Ague on igneous and metamorphic. I've given you the page numbers. If you have a different edition, the page numbers might change a bit, but this is the book that you should refer and try and understand yourself. As I told you, there are many fine points in the diagram, but I don't think I have a lot of time left to finish this course, so I refrain from doing it. But it's your business to read it. Thank you.